Right, options time then. Options. Let's start at the beginning. Alternating currents. Let's go. Describe, if at all, the reactance of an inductor and the resistance of a resistor vary with frequency. So reactance of an inductor is just given by omega L. So it is there, which is of course 2 pi f L. So therefore it's proportional to the frequency. A resistor, on the other hand, doesn't vary at all. So 2 marks here. Reactance proportional or increases with or whatever to frequency. Whereas resistance doesn't change. Resistance is independent of frequency. Probably be useful, I suppose, for you to have the right bit of the data booklet going. Yeah, so there's our expression for reactance of an inductor. Following potential divider circuit, the output PD is taken across the inductor. Okay. Calculate the output PD when the frequency is 5 Hertz. So first thing to do would be to calculate the reactance. So let me chuck that into a calculator. So we are 2 pi times 5 times 10 to the 4 multiplied by 46.9 times 10 to the minus 3. Let's chuck that in. I don't really want an answer in pi. So I've got a reactance of 1.47 times 10 to the 4. Which is 14.7 kiloohms. Okay. And then I just need to calculate what fraction of the total PD. So this is a potential divider, but we do have to be a little bit careful combining because this isn't a resistance. Bear in mind, this is a reactance. It is not a resistance. So what we want is that reactance, 14.7 kΩ, divided by the impedance of the circuit multiplied by the input. So if you bear in mind, the sort of potential divider formula looks like this. It's a kind of R1 over R1 plus R2 V in. But the problem we've got here is we're not adding two resistors. We're adding a resistor and an inductor. So we need to change R2 to the reactance, but because of the phase difference between these, we need to add them like that. We need to take RMS. So that's so 14.7 over square root 14.7k squared. I really shouldn't be using k, should I? Let's go times 10 to the 3. That's pretty bad practice, isn't it? Times 10 to the 3 squared plus 12 times 10 to the 3 squared. I mean, arguably, all of those times 10 to the 3s are going to disappear out of my calculation, and it's not going to matter. Multiply that, of course, by the input PD. So basically, fraction of the total impedance that is represented by the inductor divided by sorry, multiplied by the input is what we're going for here. Let me just chuck that in the calculator. So what have I got? 14.7. And that's over square root 14.7 squared plus 12 squared multiplied by it 0.2. It gives me 6.35 volts. Okay. So what happens to the output PD when the frequency is increased above 5 times 10 to the 4 hertz? So what's going to happen here is because if we look at our equation here, reactance is we've already stated that reactance is proportional to frequency, so therefore that reactance will increase, and this is going to take a larger share of the input PD. So basically it's going to increase is what's going to happen. It's only 1 mark. I don't think we need to say more than that. Output PD, yeah, it's just going to increase. It just says state, it doesn't say explain, so I think we're done. Okay, potential divider circuit. Again, this is essentially the same question, isn't it? But with a capacitor instead of an okay. Slightly different. Anyway, calculate the reactance of the capacitor. So over on the right hand side, there's my expression for reactance of a capacitor. It's 1 over omega c. So 1 over, so x equals 1 over omega c, and omega of course is 2 pi f. And the capacitance is 216 picofarads. So be careful with the pico, that's times 10 to the minus 12. If in doubt, I believe they are listed on the formula sheet somewhere, aren't they? Here we go, 10 to the minus 12. You can always check, don't, if you're not 100% sure. Okay, 1 over that lot. Let me just calculate that. Times 5 times 10 to the 4 times 216 times 10 to the minus 12, and that is also equal to 1470 ohms. Oh, sorry, 14700 ohms. 14.7 kilo ohms. Okay, explain why the output PD decreases with frequency. For 2 marks here, so 2 points to make. So the first point we'll make is that the reactance will decrease with frequency. So reactance is proportional to 1 over f. So decreases with frequency. And then the second mark, we need to make clear that we understand how this potential divider circuit works. So there's my first point, and my second point is going to be something along the lines of therefore its share of PD drops. Share of total PD decreases, or fraction of total PD, or something along those lines. Yeah, arguably you could, a longer, I think for 2 marks that's enough. If I was going to give a longer explanation, I would probably say, therefore total impedance of the circuit decreases, so current increases, so the PD across the 12 kilo ohm resistor increases, and the PD of across the 2 must add to 0.2. That's the long version, but for 2 marks, I think it's okay to just say fraction or share of total is going to decrease. Explain briefly why the following circuit has a Q factor slightly greater than 1, and why 5 times 10 to the 4 hertz is the resonant frequency. So 2 parts to this question for 2 marks. The Q factor is slightly greater than 1. The Q factor is given by that the PD across the inductor over the PD across the resistor or across the capacitor. So I think if we just kind of quote that, Q equals VL over VR, which is proportional to reactance over R, and that is equal to 14.7 over 12, which is greater than 1. I don't think we have to. It says explain briefly. I haven't actually used any words, but I think that's probably okay. The Q factor is greater than 1. We've shown that that's true. Explain why that is the resonant frequency. So at the resonant frequency, bear in mind these two are completely out of phase with each other. So at the resonant frequency, what we have is that the PD across this is the negative of the PD across this, and therefore we have like maximum current in our circuit. So yeah, we just need to say something along those lines. Equal reactance I suppose equal reactance for inductor and capacitor at that frequency. So resonance. Hopefully that's enough. Sketch a graph of current against frequency for the circuit shown. Only 1 point needs to be calculated. Space for calculation. Okay, so what we need to calculate, this is a current against frequency graph. The general shape of this, it's going to come up from 0, it's going to peak, and then it's going to tail off like a resonance graph. We, I guess, need to calculate where the peak is. So we already know the frequency. Oh my goodness. The frequency is at 50 kilohertz, 5 times 10 to the 4 hertz. So the frequency, the peak is somewhere on this line. Space for calculation. So yeah, what happens, the reason these hit a resonance, as I mentioned, it is the antiphase of the PDs across these two of the reactances. The antiphase of those will essentially mean that the PD across this and this cancel each other out to be 0. So all of this 8.2 volts will be across the resistor. So the current therefore is just equal to 8.20 over 12 thousandths, which is 6.83 times 10 to the minus 4. Which is about 0.683 milliamps. So, yeah. So there. So I need to pass through that point. My drawing skills are going to be horrific here. The frequency, when the frequency is 0, the current will be 0. Because obviously if this frequency doesn't change, the capacitor just charges to meet 8.2 volts, and then all current stops. So it is 0 at 0, and then it's going to come up, and oh goodness, that is not great, but I'm kind of hoping that I could do better on paper, but maybe not. I think our resonance curve won't come back down to 0, but it will tend in that direction. to 0. Yeah, that's the kind of, it's the same as any sort of resonance graph that you draw. Okay. I can only apologize. The ideas are correct, I hope. What is happening here? Harry is asked by his teacher to sketch an oscilloscope trace for a sinusoidal power supply of RMS 20 millivolts and frequency. Okay. He is expected to suggest sensible values of the volts per division and of the time base. His answer is shown below. Determine to what extent he has answered correctly. Okay, I think I know what's expected here. So volts per division, let's see, we have 1, 2, 3, 4 at 5 millivolts. 4 times 5 millivolts equals 20 millivolts. 20 millivolts peak. But the supply is RMS 20. Is 20 volts RMS. Sorry, 20 millivolts RMS. So yeah, there's quite a lot of marks for this. So I'm guessing we're going to have to do some other calculation here. I would suggest we either need to calculate what RMS value this gives, or calculate what the peak value of this is. So peak V should be at, and it's going to be 20 millivolts times root 2. Which is, I could probably manage that in my head, but anyway, 28.3, somewhere about there. .3 millivolts. Therefore, he is incorrect. So should use, well, the next one up is 10 millivolts per division. Let's have a look then at the time base. That's set to 1 microsecond. So 1, 2, 3, 4, 5. Period of trace equals 5 times 1 microsecond. So 5 microseconds implies frequency of 1 over that. I'm running out of space. 1 over that, which is, goodness me, 2 times 10 to the 5, of course, isn't it? Probably could have managed that in my head. 2 times 10 to the 5 hertz, which is indeed 0.2 megahertz. So correct. Yeah, or so sensible, because it shows a whole trace, I suppose, is because it's asking sensible values. You know, and you could change this and it's still going to display the whole cycle if you had a much higher time division. I don't know, so sensible since shows full cycle clearly, something like that. Okay, that's it.